Good morning, and I'll be looking at support vector clustering today, which is essentially like it's a clustering algorithm leveraging the principles which we have learned from support vector machines. So we'll start with a definition of a mathematical problem called a minimum enclosing ball learning problem, right? Just like the hard support vector machine classification problem, SVM problem, hard SVM problem, we'll be looking initially at hard MEB problem. MEB stands for minimum enclosing ball. Let's look at this problem called hard MEB problem. The problem is very simple. You are given and we are looking at clustering algorithms. So let's assume that we have unlabeled data for which we don't know the labels. So the hard MEB problem is stated in the screen here, which is given a set of points. The set of points are labeled as the set S, containing x1 to xm, such points, where each of these xi is represent the r-dimensional real space. Right? These are all these xi's are vectors essentially, like d-dimensional vectors. The minimum enclosing ball problem, or MEB, minimum enclosing ball of the set S, is the smallest ball, you can call the smallest sphere that contains all the points in S. That problem is called the minimum enclosing ball problem. You are given a set of data points, you want to find a ball which encloses all the points, everybody is inside. You want to find a ball which essentially marks the periphery, right? You want to find a ball which essentially contains everybody. And that problem is called an MEB problem, minimum enclosing ball problem. I hope this point is clear to you, right? MEB problem, hard MEB problem. Right? So you can see this here. You have a set of points, and you want to find a sphere in the two-dimensional space, a circle. Right? You want to find that circle with the minimum radius which encloses everybody, which contains everybody, right? So some of those points will essentially mark the boundary. And you have even labeled the radius of that sphere or that ball, or in this case, a circle in the 2D space as R, right? That's called R. That's labeled as R, all right? So we have heard of the concept of a kernel-induced feature space or a high-dimensional feature space, which is essentially RK, just reproducing kernel Hilbert space in the case of support vector machines. So the natural question is, okay, we have got data represented in some data space or an input space, and if we assume that there is a mapping phi from the input space, which is primarily the vector of x's, the xi vectors, if there is a mapping from the input space to a high dimensional feature space, can we learn such a sphere in the feature space? If yes, that would be interesting, right? Rather than learning the MEB, which we have seen in the input space, can we learn the MEB in the feature space, right? If that is the case, what are we looking at? We are looking at a sphere which encloses everybody, and we are looking at that problem in the feature space, not in the input space. You can do that in the input space also, but we are interested in looking the MEB learning problem in the feature space, in the transformed data space, right? So how does that problem will look like? I want to find that sphere, that minimum enclosing ball. Minimum meaning minimum in terms of the radius. So minimize that radius, right? For convenience, you have put the square of the radius. Minimum r square says that. What is my agenda? All right. Phi of xi. What will be phi of xi? The representation of xi in the feature space is called phi of. In the feature space is called phi of xi. That's what. So xi here getting represented as phi of xi here, right? And if mu is the center of the sphere, if the center of the sphere is labeled as mu and r is the radius, I want to find that sphere in the feature space where the center is mu, and my agenda is I want to find that sphere with the minimum radius such that everybody is inside. Which means that phi of xi minus mu. Have you seen this symbol? This is Euclidean distance. The Euclidean distance between phi of xi and mu, which is the center, that is the distance of the point xi represented in the feature space from the center if that distance square should be less than or equal to the square of the radius. Basically, square of that distance should be less than or equal to the square of the radius, right? Which essentially says that everybody is inside. Give me that sphere with the minimal radius where everybody is inside. That's a statement of this final problem, right? My MEB problem is stated like this. Find the minimum enclosing ball. It's the smallest ball. Smallest. How do you define the notion of smallest? In terms of you can define that in terms of the radius. You can say, get me that sphere with a minimum radius where everybody is inside. That's being mathematically represented over here. Get me that sphere in the feature space with the minimum radius where every data point is within the sphere, which means that the distance to every point from the center is less than or equal to r, or for convenience, you have represented the square of the distance. Basically, you can look at the Euclidean distance and see that everybody is inside, and that should be true for everybody, for all I. So this is the sphere, is the MEB learning problem, hard MEB learning problem represented as an optimization problem, right? And you can see that this is nothing but a convex quadratic problem, right? As very similar to the SVM problem, right? It's a quadratic function with constraints which are box constraints, which is less than or equal to convex, right? How do you solve this problem? You go for Lagrangian representation. You will go for, so here, right? We have a primal problem just like SVM. How do we solve this hard margin problem? We can write the Lagrangian equivalent. We'll go for the Wolffied duality. We'll write the Lagrangian. Lagrangian is essentially like, you will write that, right? Minimum Lagrangian is r square plus sigma is equal to 1 to m alpha. I introduce the notion of Lagrangian multipliers alpha I into right, phi of xi minus mu minus r square is less than or equal to 0. That's a way in which Lagrangian, primarily converting that constraint optimization problem into a Lagrangian form, and then and where every Lagrangian multiplier has to be greater than or equal to 0. That's the definition of a Lagrangian. Once you have the Lagrangian, and this is a convex quadratic problem, the KKT, the Karish-Kundaker conditions, becomes a necessary and sufficient condition, which has the first order condition as well as the complementary slackness conditions. So what we do is, what are the variables over here in this problem? The variables are r and mu, right? R and mu. R is the radius and mu is the center, right? What do you do? You apply the Karish-Kundaker conditions with respect to the variable, the primal variables r and mu. So the first order conditions are dou L by dou r is equal to 0 and dou L by dou mu is equal to 0. Dou L by dou r is equal to 0 will give you 2r minus 2r into alpha. See, basically dou L by dou r, right? This term will remain 2r into basically alpha, sigma alpha will remain. So 2r into sigma alpha. 2r into sigma alpha is equal to 0, which essentially will give you 2r is equal to 2r into whatever. So sigma alpha is equal to 1 is what you get out of dou L by dr, the first order condition, with respect to the primary variable r. Right, the other primary variable is mu. Dou L by mu is equal to 0 will give you this kind of equation, which is essentially like, you can look at it. So minus, right? It's minus that minus of minus 2 into alpha into phi of xi minus 2. So essentially minus 2 into alpha into phi of xi minus mu is equal to 0. So you know that mu is essentially like, so mu summed over, you see, if you take that to the other side, what you get is what you call sigma alpha phi xi is equal to mu is a kind of equation that you get. All right. So, and the complementary slackness conditions, as always, which essentially says what you call, and you must have seen that there are some like kind of constant factors here, because mu summed over, you can see that mu summed over m, which is 1 by m. That factor is ignored here. It's basically just 2. It doesn't what you call come into play. So there is a 2 and all that. So you can actually what you call ignore if you want. So that's a kind of context out here. Sigma alpha phi of xi into sigma alpha into mu. So I mean, if somebody from mathematical background in mathematics will easily realize that there's some constant factors over here. So we just ignore for the representation convenience. So complementary slackness conditions are essentially alpha I into this should be 0. Right? From here we can see that there are two cases. Alpha I can be 0. If alpha I is equal to 0, what will happen? If alpha is equal to 0, what will happen is, if alpha is 0, this has to be, this will be less than or equal to 0. That means phi of xi minus mu is less than or equal to r square. So alpha is equal to 0 are the points which is essentially falling inside, and alpha is equal to, alpha is non-zero. If alpha is non-zero, what will happen? This has to be 0. If alpha is non-zero, as per the complementary slackness condition, this has to be 0, which means that phi of xi minus mu square is equal to r square. So alpha I is equal to r square will be those points which essentially represent the sphere, right? So you can see that mu is represented over here. So the Wolff-Duell form, how do you get this? You apply what you call, I have given you for the SVM. So you just substitute for r and mu in this here, and then you say max cell with respect to the alpha greater than or equal to 0, and you write the Wolff-Duell equivalent, which is something that I've already worked out for you in the last class. You get in the class 7. You can look at the notes and you can write very similar equations over here. So max cell with respect to the constraints are there, and you get this as the Wolff-Duell. So how do you? So you have a primal problem over here, and corresponding the primal problem over here, and corresponding primal problem, you got a dual problem, which is in terms of where which is in terms of the Lagrangian multipliers, where Lagrangian multipliers becomes the dual variables, and and you can see that we have done that problem in terms of in the feature space, which is the transform space, where phi of xi becomes a representation. And so essentially you get the kernel also. So you get phi of xi dot phi of xj. You can see it here, right? Phi of xi, and if you multiply see, so for example, alpha I into phi of xi. So phi of xi is essentially you get phi of xi into this particular term, right? So if you apply it back and r square, so for example, you have a term in r square. So you need an expression for r, and you substitute it back essentially. That's what it is. And so we'll show you like how do you get to r. That's another thing that we are going to see. Like we don't have an expression for r over here. How do you get to r? You know that the points. So phi of xi minus mu square is equal to r square when alpha is non-zero, which means that if you can identify the points with alpha non-zero, those are the points which essentially mark the boundary, right? Essentially, like those are the points with the Euclidean distance from their transform space. In the transform space, the Euclidean distance from them to the mean, right? Phi of xi minus mu square is equal to r square means they essentially like phi of x square minus mu is equal to r square. So these are essentially the points which defines r. So how do you get r? You find the average distance of the points where the alpha values are non-zero, right? That's how you compute. So essentially, like you get an expression of, so r square, you got phi of xi minus mu square is equal to r square, which means that r is equal to phi of xi minus mu, right? Essentially, the Euclidean distance to those points where the alpha values are non-zero. That's how you get the expression for r. We'll come there, right? So all I want to say is, we have defined your MEB learning problem as a primal problem, and you have derived the equivalent Wolff-Duell form, and there since you have phi of xi dot phi of xj terms, which can essentially get represented by the kernel functions that we have discussed in the last class, which essentially are Mercer kernels. So kxi, xj is a kernel function giving phi of xi dot phi of xj. So essentially, instead of doing the explicit transformation phi of for every xi as phi of xi to the feature space, what you can do is you can compute their dot product, the dot product needed for this MEB computation in the original space itself using kernel functions, and you get a kernelized form of representation. Right? So using kernel functions, you compute phi of xi or phi of xj. All you do is you don't do any explicit transformation. You get the corresponding computation achieved in the feature space. So instead of solving the primal problem, you solve the dual problem, which in turn, in which the primal variables r and mu in turn get represented by in terms of the Lagrangian multipliers, which are essentially controlled by the number of data points that you have in place, where the other one is mostly in terms of is defined in terms of feature space. So that's a map behind it, and let's get into we have seen Gaussian kernel, which is essentially like it's a similarity function where Q is a defined parameter, which is something that I've already shown in the last class. What is support vector class? right? What is support vector cluster? I just gave you the idea of an MEB problem. An MEB problem being represent the primal space, and how do you derive the equivalent Wolfed even, and how the parameters play out. Primarily, the primal variables and the real variables are identified primarily, and then apply the first order necessary conditions, which are essentially defined in terms of the KKT conditions, because the problem in hand is a quadratic problem, and they are necessary and sufficient conditions in that context. All right, it's very similar to the SVM problem. What is support vector clustering? That's our general SVC, support vector clustering, right? In SVC, the only difference that an SVC has with an MEB problem is we allow points to fall outside the sphere. We will allow, see, instead of what you call asking everybody to sit inside, you can say, okay, if certain points in the feature space, when the transform space can go out, let us learn the MEB in the transform space, where we allow certain points to fall out. All right. So very similar to the soft SVM problem. All right. We have a modified form of the MEB problem where we allow points to fall out, but there is a penalization. We will penalize all those points which make mistakes. All right. So zeta I is the parameter which captures the extent to which they make mistakes. And for every point, and there is a constant which is essentially the cost function. If C is very high, we don't allow anybody to make mistakes. If C is low, which says that yes, we can afford to have mistakes. So we have very similar problem, min R square plus a penalization term, where and now we say that phi of xi minus mu. That means the distance of any point in the transform space to the mean, which is essentially the Euclidean distance in the transform space for any point to the mean, the square of that should be less than or equal to not just r square plus zeta. So it should be like the radius plus the mistake that it makes. Zeta can be more than it can be 0 or more, right? Zeta I is greater than or equal to 0 for all I, right? Where this is a penalty term introduced for allowing certain points to fall outside. That's the only difference compared to an MEB problem. And what is the next step? This is the primal problem. And again, you can see that this is a quadratic problem. And what you do is you apply Lagrangian. You go to the Lagrangian duality. You write the Lagrangian for it. So what you get is R square plus C summed over zeta I, phi of. So you write this expression as phi of xi minus mu minus r square minus zeta I is less than or equal to 0. That's the way in which you typically write your constraints when you want to write the Lagrangian, and then you apply the complementary, essentially like alpha I into that Lagrangian multiplier into that constraint. So I think that constraint is basically plus. There is one more term. So phi zeta I is greater than or equal to 0. It has to be written as minus zeta I is less than or equal to 0 when you write Lagrangian. That's a standard form in which you represent your constraints. So basically your constraints will be represented as what you call your constraints is less. Basically like your AX is less than or equal to 0 form. That's a typical where AX is less than or equal to the standard form. And so minus zeta I less than or equal to 0 is equal to 0, which will be represented as with another Lagrangian multiplier called beta I, very similar to the SVM soft margin case, beta I, zeta I. So that will be the case. And constraints are Lagrangian multipliers alpha I and beta I, which are essentially introduced for all I should be greater than equal to 0. So that's what the Lagrangian form is, which is soft margin, I would say soft MEB problem, right? You apply first order conditions, which are Karish-Kuntaker conditions, KKT. What are the primal variables over here? We have got R, mu, and zeta I now. So you apply the first order conditions, which are first order necessary and sufficient conditions, because the problem in hand is a convex quadratic problem. KKT becomes the first order necessary and sufficient condition. So dou L by dou R is equal to 0. Very similar to, you can look at the math, which is pretty straightforward if you understand differentiation. So 2R minus, you can see that 2R minus, there is another here. 2R minus 2R alpha, sigma alpha I is equal to 0, which will essentially give you alpha I, sum over alpha I is equal to 0, and dou L by dou mu is equal to 0, which is the next condition with respect to the primary variable mu will give you this kind of equation. Mu will be defined like this. So there is no difference, and dou L by dou zeta I will give you is equal to 0, will give you C minus zeta I minus beta I is equal to 0, which means that alpha I plus beta I is equal to C, right? Which also is very similar to the soft SVM case. Alright, complementary slackness conditions will be beta I zeta I is equal to 0 and alpha I into 5xi minus b square minus r square minus zeta I is equal to 0. It's a part of the case. Right, the Wolfe dual, when you apply it back, you get this kind of dual, and which also is very straightforward. The only difference will be here, right? The constraints, the alpha is in between 0 and C. So what are the cases? Alpha I can be 0, alpha I can be between C and 0, and alpha I can also be beyond C, right? If alpha I is equal to 0, what will happen here? If alpha I is equal to 0, what will happen? Beta I is equal to C. If beta I is equal to C, alpha I is equal to 0, beta I is equal to C. If beta I is equal to 0, from the beta I is equal to C, that means beta I is C, which means that zeta I has to be 0. So alpha I is equal to 0 says that zeta I has to be 0. What is zeta I? Zeta I is the mistake. Mistake has to be 0, right? Alpha I, we know that alpha I is equal to 0, right? Alpha I is equal to 0. I'll just go back. Alpha I is equal to 0 gives you beta I is equal to C. Beta I is equal to C means beta I, zeta I has to be 0. So zeta I has to be 0. Alpha I is equal to 0 says zeta I is equal to 0. Zeta I is equal to 0 here also. Alpha I is equal to 0, which means that alpha I is equal to 0, which means that phi of xi minus mu minus r square has to be less than or equal to 0, which means that phi of xi minus mu square has to be less than or equal to r square, which means that alpha I is equal to 0 are the points which are well behaved, meaning essentially they are inside or like on the periphery of the sphere under consideration. What is the next case? Just like the soft margin case, alpha I can be between C and alpha I can be between C and 0. If alpha is between C and 0, alpha I is between C and 0. Alright? So alpha is between C and 0. What is beta I? Beta I is equal to C minus alpha I. Alpha I is less than C. Right? Is between 0 and C. Alpha I is less than C, which means that C minus alpha I will be positive. So beta I will be positive. If alpha I is between 0 and C, beta I will be positive. If beta I is positive, what will happen? Zeta I will be 0, because zeta I has to be 0 as per the complementary slackness condition. So which means that beta is positive, zeta I is 0. So zeta I is equal to 0. Alpha, we know that alpha is between 0 and C, which means that alpha I is positive, which says that so this is positive, which says that this has to be 0. Where we know that from the previous observation, this is 0, which means that phi of xi minus mu square is equal to r square. So the points which are for which alpha I is between 0 and C will have phi of xi minus mu square is equal to r square. What does it mean? It means that those are the points which actually falls on the boundary. When alpha I is equal to 0, what will happen? Alpha I is equal to 0, which means that this will be 0. That means beta I will be 0. Beta I will be 0, which means that zeta I can be greater than or equal to 0. Alpha I is equal to 0 says that beta I will be 0, which basically like beta I is equal to 0, which means that zeta I, there is no restriction on zeta I. Zeta is, we know that zeta is greater than or equal to 0, which means that zeta is greater than or equal to 0. So this term will exist. Alpha I is equal to 0, which means that this has to be 0, which means that phi of xi minus r square is less than or equal. Alpha is equal to 0. This has to be 0. This has to be 0. That means that phi of xi minus mu square minus r square minus zeta I is equal to 0, which means that phi of xi minus mu square is equal to r square minus r square is equal to r square plus zeta I, which means that these are the points which are essentially outside, which can essentially make mistakes. So there are three classes of points here. Alpha I is equal to 0 are the points which will be inside. Typically between 0 and C will lie on the sphere, and points which lie outside the feature space they are essentially called the bounded support conditions in the case of supported clustering. Bounded support vectors, right? BSVs, they are essentially points that are outside the feature space sphere, right? So, but after Understanding all this, back to our original question, how do you define R, right? What is R? R is a sphere, a radius of the sphere. R is a radius of the sphere enclosing all the points which are well behaved essentially, right? As per our definition, R will be like the distance to those points where, right? What is alpha I is equal to 0? Right? Alpha I is equal to 0 will denote those points which lies on the sphere, which will define the sphere. So for those points, right, which define the sphere, their distance g of xi, right, that is distance to those points which define the sphere. G square xi, you know that is nothing but the distance to a point xi from the center is phi of xi minus mu square, right? So phi of xi minus mu square, you can expand it. This will be k xi minus 2 whatever. This is the kind of form that you get, right? This is the kind of form that you get when you expand it with the kernel function out there. So you can compute R also. You can compute R as the distance to those points for which your solution to the unified dual problem, K mu alpha is between 0 and C. That's how you find R, right? Good. So what is supported conditions? Let's go back to our original problem, right? Which is essentially learning learning clusters with these kind of MEV based approaches. So support vector clustering says that yes, let me learn a problem in the original in the feature space. Let's go back to our original case. We have a problem. We have your data defined in the data space. Without an explicit transformation, you have learned that you can actually compute the MEV in a feature space using kernel functions. What happens if I found the MEV, which means that I know which are the points which are falling on the boundary. Right? Can this boundary be mapped back to the original space? If I map the boundary back to the original space, if I repeat, if I map the boundary points only, if I map the boundary points back to the original space, what will happen here? It will form some contours. There will be some contours. And in SVC, we say that, right? That's the definition of SVC. If from the feature space sphere, if we map this boundary back to the original space, right, to the original space, what will happen is we'll get some contours, and those contours are defined as clusters. So supported condition says that we have a problem in the original data space. Let us, instead of finding what you call the minimum enclosing ball here with some allowance, with some permission for somebody to fall outside, let us learn the MEV in the feature space, in a transform space, which is achieved using some kernel functions. And once I find that MEV, let me map back this boundary to the original space. In that case, what I get is the points which are on the boundary will form some contours here, and I define those contours, the points which are enclosed by those contours, as the clusters. That is the definition of supported clustering. So if we map the points in the transforms, which we map the points in the boundary of the feature space sphere to the original space, we will get some contours, and the points enclosed by those contours are defined as clusters. That's the definition of supported cluster. Right? So once you have done all these exercises, learning an MEV problem and allowing some points to fall outside, we get some the sphere there. And can we map the sphere? That's essentially the points which define the sphere back to the original space is the problem in hand. If we do that, we get some clusters, and that's how SVC defines the clusters. How do we do that? This is a computationally intensive problem, and it applies principles from graph, a little of graph theory, right? In SVC, the contours that encloses the points in data space are defined by, how do you define the contours? So your sphere in the feature space are at a distance of the points that are at the boundary of the sphere are at a distance of R, right? The points which are at a distance of R is essentially the points which are at a distance of R is essentially define the sphere, right? How do you identify those points? When you solve that dual problem, you have identified those points as points with alpha is between 0 and C, right? So contours that enclose the points that in the data space, which is essentially the clusters, are those points which are at a distance of R, right? Which at a distance of from the center of the sphere in the feature space. If they are at a distance of R, they are the contours, right? If we can identify those points which are at a distance in the feature space, right? At a distance of r in the feature space, you know like which are those points define the contour, right? That's the computation in the high dimensions feature space and the reverse mapping, right? All I need to do is I need to identify those x's in the original space where the gx is essentially the distance of those points from the feature space sphere, which is essentially the distance of those points from the center of the feature space sphere is at R, is positioned at R. Essentially, the points which are at the distance of R from the feature space distance. And we know that those points are essentially the points with alpha is equal to 0. If we can identify those points, we can easily identify those points because we know that those points will have values of alpha at is between 0 and c. So we know those points. That's the computation. So, and we know that this gx is essentially computed in terms of with only the kernel. We don't do an explicit transformation, which means that the computation in the high dimension space in the SVC, what we do is we map the original data points. We don't do explicit mapping. We assume that there's a mapping from original data space to feature space. We do the computation of the features, the sphere computation in the feature space. We map the boundary of the sphere back to the original space, and they are the contours. They are the essentially the clusters. So essentially, we do all this computation with the help of kernel functions. Thus, the computation of the high dimension feature space and mapping back to the original space to find the contours is achieved only with the kernel function without doing explicit transformation. So this SVC is also an example for a kernel for an algorithm which uses what is called kernel trick. All right. So how do you assign? Right, your agenda now reduces to find those points x's. Once you have an optimal primal problem, you have found the dual problem, you solve the dual problem, you get the Lagrangian values, and now you know that the points for which the Lagrangian values are between 0 and c are essentially the points which are on the boundary, and I identify those points. And the only thing that and there are other points also. So and we map the boundary back to the original space. Alright. So there are points which are inside. There are points which are inside. There are points which are outside. How do you assign those points? You need to assign those points also to the cluster, right? That's what it is. So essentially, if I map the feature space sphere back to the original space, I can find contours. But contours will only map the boundary of the clusters. But I need to assign the points which are inside the sphere is there, points which are outside the sphere is there. How do you do a cluster assignment? That's the most critical problem that SVC asks now, right? We know that cluster boundaries are defined by the contours, which are essentially the boundary points in the feature space, MEB. But they define only the boundary, right? How do you assign the other points? And that is called the cluster assignment, which uses a little involved map. So it employs a geometric method involving gx, which is essentially the distance between any point and the center in the feature space MEB, which is the center mu in the feature space MEB, based on the observation. Given a pair of points, let us take any pair of points from that data set, right? I've got points x1 and x2, for example. I can take any pair of points, say xi and xj, x1 and x2, x3 and x4, from the data set, from the available data set, which is we assumed right in the beginning that these are unlabeled data points. We take any pair of points, and we can actually we can sample between the points here, right? How do you sample between the points? I can get the midway by x1 plus x2 by 2, and any ways where any convex combination of x1 and x2, you get a point in between, right? That's what it is. So you can find any point in between. You sampled, right? Every point in between. There are infinitely many points. You can't do that. You just sample. Say, for example, between x1 and x2, I can take samples. Let's assume that let's take 100 samples between x1 and x2. And what I can do now, I've got points xi and xj or x1 and x2, and I can find 100 samples which are between x1 and x2, which are not points within the data set currently. I'm taking 2 data points, x1 and x2, from the data set, and I can sample points between x1 and x2, right? I'm sampling 100 points, and I can find the distance of each of these 100 points, right, from the feature space center, MEB, or center of the MEB, right? I've got an MEB in the feature space, and I know I have an expression for gx, which we know already. What is the expression for gx? We know the expression for gx. Gx is here. So for every computed point between an xi and xj, I can find gx at any point, right? For any pair of xi and xj, I sampled 100 points in between, and I check the distance of each of this point from the center of the feature space MEB, which is essentially Gx. If I see that at any point for any of these 100 points in between xi and xj, if Gx is equal to R, what is the indication? Which means that some point between the pair of points xi and xj is hitting the boundary. Alright, and our boundary is essentially, what is boundary? This boundary in the feature space MEB is essentially defining the boundary of the contours enclosing the clusters. Which means that if the line connecting these 2 points, right, at any moment, if the line connecting these 2 points xi and xj, right, has a point which hit the boundary, which means that these 2 points are not belonging to, because it is this point, that point which is at a distance of R, right? The point which is in between, in the line connecting xi and xj, if any such point is at a distance of R, which says that these 2 points are essentially, if we had all these points in the data set, some of these points would have actually hit the boundary, which is essentially marking the boundary of the clusters out there. Which in turn says that these 2 points cannot belong to the same cluster. Right? That's being applied here. Given a pair of points, that's a statement. Given a pair of points that belongs to different clusters, any path that connects them must exit from the sphere in the feature space. They will have a, see, between xi and xj, if we look at the line connecting xi and xj in the 2-dimensional space, if any point in that line, we can only sample and test. If any point in that line is exiting from the feature space sphere, which is an indication that these two points xi and xj cannot belong to the same cluster. That's a definition, right? Because I mean the logic behind that is like, which means that that point is actually hitting the boundary, which means that they are hitting the boundary. The boundary of the sphere is essentially the boundary of the clusters out there, right? And which is saying that these 2 points, like if they connect these 2 points together in that feature space, that like hit the boundary, which means that they are in different clusters. Given a pair of points that belong to different clusters, any path that connects them must exit from the sphere in feature space. So now what we do is we define an adjacency matrix, which is essentially like the graph representation. M between pair of points xi and xj. For every pair of points, if I've got m points, you will construct an m by m matrix, right? Between each pair of points xi and xj. Alright, what you do is define an adjacency matrix M between pair of points xi and xj, whose images lie in the on the sphere in the feature space by looking at the image of the path that connects them. Essentially, like you look at the convex combination of those points which are in between in xi and xj, which is essentially like you look at every point, right, between xi and xj, which is we call it y. If the distance of y is less than or equal to R, which means that no point in the line joining xi and xj, right, crosses R, which will say that hey, they are in the same cluster, right? Which means that xi and xj can be assigned to the same cluster, right? If they exist, if any point in xi xj in the line joining xi xj is greater than R, which means that xi and xj cannot be in the same cluster. Which means that after this computation, using the distance of every point in the line joining for every pair, right? You have got 100 points in the data set, which means that 100 C2 such computation has to happen. And in 100 C2 such computation, each of this computation, you have to sample, maybe like let's assume that if you are sampling 10 points within each pair of points, you have got 10 into 100 C2. That will be the kind of computation, right? Once you do that, you get a what do you call? You get an adjacency matrix. And what this adjacency matrix says, if points I and j in the original data are in the same cluster, you will have one in the adjacency matrix. So ij is connected, and ij is connected, j is connected to jk is connected, which means that ij will have connectivity, jk will have connectivity, kl will have connectivity, kl is not connected. That means that one won't be there. So once you have considered such an adjacency matrix, the problem reduces to clusters that are now defined as the connected components of the graph induced by M. So if we represent M, the adjacency matrix in a graphical form, see ij is connected, jk is connected, but kl is not connected. So ijk, that forms a cluster, right? So clusters can be easily identified by a connected component analysis of the adjacency matrix representing the graph in this context. So the points that lie outside, so that will work for every other point. So, but we have seen that there are points which are falling outside the what do you call, the sphere, which essentially like will not be typically considered. You will, because you are only considering points with alpha is equal to 0 and alpha is equal to is between 0 and c, and those points which are outside the boundary, what you do is you can do a what you call nearest neighbor assignment for the BSVs, which are for which alpha is equal to c. SVC typically, what SVC typically does is they'll assign points to the closest what you call clusters, because for those points you are sure, right? See, if you are taking every pair of points, I mean one point from here and which is essentially like what do you call which is inside, and another point for which what do you call the it's a boundary support alpha is equal to 0, which you are sure that you'll essentially exit, which means that they are always outside. So you'll never ever get what you call. If you are taking 2 points which are outside, 2 points which are for which alpha is equal to 0, what will happen? Right? They'll be always outside. So typically, right? That's or else you'll just it'll be always outside. They'll be always in the outside category. So how do you do it? You cannot assign. So BSVs you don't typically do. You will restrict this particular computation to alpha, to points where alpha is equal to 0 and alpha is between 0 and c. And for those points for which alpha is equal to c, what you do is you do a nearest neighbor assignment after the other clusters are identified. So that's pretty much about SVC. I know that this is not very trivial when it comes to somebody who doesn't have much of what you call understanding on mathematics, but it's an interesting algorithm to look at. And I urge you to look at this, and if you have any concerns on understanding, if you are facing problems, let me know. Let me stop recording here.